Hi, this is an example problem, the electric potential of a point charge. So far in chapter 19, we've mostly been looking at how charges are influenced by the electric potential, how it changes their electric potential energy, etc. However, the electric potential itself is generated by other charges. We call these source charges. Before, we've ignored them because they're just fixed in place and they create this electric potential landscape that can influence other charges in the space around it. Here we're going to look at how a source charge generates an electric potential throughout the space in its vicinity. And we're going to do it for the simple case of a positive point charge, or any point charge. In this case, we've got a single positive point charge. You can see the image there. It's located at a certain spot, and we're going to try to figure out what's the electric potential nearby at different spots. We've already drawn in electric field lines in purple. They radiate outwards. You can kind of see them, right, as they would for an electric charge, positive. And we've also drawn in a few equipotential surfaces, the dashed yellow lines, because they're all an equal distance away from the point charge. They all have the same value of the electric potential. And in fact, we know that because the equation we can use for the electric potential to calculate is this one. V due to a point charge is equal to K Q divided by R. In fact, there's an equation there that we have that we can use. And so since all of these circles here, they're at the same distance r from the point charge, they have the same potential. Those are equipotential lines or equipotential surfaces. So for a point A, this is pretty straightforward. We're just going to go plug in the values here. K, remember Coulomb's constant. Q in this case is 6.5 microcoulombs. And the distance from the point charge to point A, so here it is, that distance there is 0.5 meters, 0.05 meters. And that gives us a value of 1.17 times 10 to the 6th. Now, what are our units going to be here for electric potential? Well, let's cancel a few things out. One of these coulombs, one of these meters, and now I got a Newton meter per coulomb. Newton times meter is a joule, so we do get units that we expect for electric potential. Joules per coulomb. Let's look at part B. So for part B, it says calculate the electric potential VB at point B. Same thing, now we're looking at this point here. It's a further distance, and we're going to do the exact same thing as we did before. We just got to change the distance. Same equation. And in this case, instead of 0, we are dealing with 0.15. Put that into the calculator, and we get an answer of 3.9 times 10 to the 5th joules per coulomb. So it's a little bit smaller because it's further away from the point charge, and so it's gotten weaker. Let's look at part D. Part D, we're going to transition back to what we were doing before. So this first charge, Q, positive 6.5 microcoulombs, it's fixed in place. It created this electric potential in the space around it. It's not going anywhere. It's not doing anything. We're going to go ahead and bring another charge, an electron, and see what happens to that electron due to the electric potential that the first charge created. So we're going to go ahead and which path will it move along, right? So it's either going to be A or B here, this electron. If we want it to move spontaneously, if we release it from rest, should the electron go from B to A, or should it go from A to B? Well, we know one thing. Potential is high near positive charges. It's low farther away, as we just saw when we calculated these two for A and B. And we know that electrons, they move spontaneously from low to high. So the electron is going to go in this direction. low to high spontaneously. So our answer for part C it's going to spontaneously go from the low point B to the higher electric potential at A. All right, let's look at part D. Calculate the change in electric potential energy of the electron for both paths in part C. So this will be pretty straightforward. For part D here, I'm going to go ahead and move this over a little bit where it's a little bit easier for us to see some stuff. Okay. So for part D, what are we trying to do? Calculate the change in electric potential energy of the electron for both paths in part C. So to calculate the change in electric potential energy of the electron, we can go ahead and multiply the electron, here's the electron's charge, times delta V. But we're going to do it twice, once from B to A and once from A to B. So delta PE, let's say we move from B to A, as we just said. Then I'm going to be looking at the electron charge, minus E, right? That's what electron is. And I'm going to do for delta V, I'm going to be the final position, VA, minus the initial position, VB, right? We can go ahead and put in those numbers, minus 1.6 times 10 to the minus 19th coulombs, multiplied by, what is VA? We need to remember that real quick. That is 1.17 times 10 to the 6th joules per coulomb. We're going to subtract from that VB, the number below, 3.9 times 10 to the 5th joules per coulomb. And at this point, let me go ahead and just calculate the voltage here for a second. So I'm going to leave this electron charge here for the moment. And the number here, delta V, comes out to 7.8 times 10 to the 5th joules per coulomb. In other words, this is an increase, delta V in this case. But when we multiply by the negative charge, we see that we're going to get a decrease in the potential energy. Putting that into the calculator, we get an answer, negative 1.25 times 10 to the minus 13th joules. Again, we cancel our coulombs there. So it's a small decrease because this electron's a tiny thing. Can we think about that, right? I said earlier, right, that this electron, if we stick it here, it's released from rest, it's spontaneously going to move from low to high. Another way to visualize the potential is this. Imagine, the electron is, out in space here. The blue tells you the value of the electric potential. It's low or it's flat, it's higher or it's bigger, right? At point A, it's up here on the hill a little bit. Think of this as electrons, they naturally move uphill from low to high. That's one way to visualize that. Let's go ahead and quickly calculate part E. What if we look at the change in potential energy if we're going to go instead from A to B, right? So in this case, we're going in a different direction. We're going to go from A to B. The electron is not going to want to go that way, right? Because the electron likes to be near the positive. Let's see what happens to the potential energy as we move it away from where it wants to be. Well, in this case, we've still got minus E, and now we've got VB minus VA, the opposite direction. Well, we know what that's going to be, right? Because this is 1 minus 1.6 times 10 to the minus 19th. And this is just going to be the opposite of the number that we did before. This will be negative 7.8 times 10 to the 5th joules per coulomb. We calculate that, going to be the same, except now the two negatives cancel to produce positive. We're going to get an increase in the potential energy, 1.25 times 10 to the minus 13th joules. So we end up with, in this case, the direction where the electron doesn't want to go. Well, that's the direction which gives the electron an increase in its electric potential energy. Kind of like when you pull a basketball and you move it up. It doesn't want to go up. Gravity wants to pull it down. But when you go up in the opposite direction of gravity, then you do get an increase in the potential energy.